My big pleasure to have you all here on board today for a symposium on robots in architecture. I'm just going to keep forwarding that. We have a very exclusive cast today with us. We have the Association for Robots in Architecture, Sigrid and Johannes, who have produced a 4-day workshop with us, to which I'm going to invite you as well for the 3 p.m. gig in the afternoon. But we also have representatives of people who are dealing with robotics in architecture with us. Dave Pigram from Supermaneuver. We have James Gardner and Stephen Johnson from the Engineering Excellence Group. We have Rob Beeson and Gabe from ARMA here with us. And of course, we have Rob Saunders and Petra Gemeinberg. Now, what I wanted to do now is to just very quickly let these slides run while I give you a bit of the backup of what we have been doing in the workshops and the way we are seeing this symposium today. It doesn't seem to be on automatic timer, which is a sort of bit of a pity. Okay. Now, robots in architecture, that is something that is very interesting, obviously, because it deals with the idea of digital fabrication. But robots in architecture also answers a different call towards how do we understand architecture today? How do we understand construction? How do we understand digital fabrication? What is the purpose of these robots, and what do they affect in the modes, in the practice, in the thinking, and the design, and in the construction of architecture itself? These are things for which we have handpicked these 4 people who will give us different lenses on the way in which they're seeing robotic and robotic fabrication in architecture. From the very complex design processes through parametric and scripting exercises towards the applied fabrications in digital manufacturing, with an research that is actually undertaking in an applied environment, towards the interfaces of architecture and construction and robotic fabrication. So someone who operates at the intersection, translating the architectural design towards manufacturing processes. And then at the end of the day, towards robots and robotic interactions that engage the audience in curiosity, in sensing, in inquiries that challenges necessarily the identity of people when they interact with robots who are in the performances their counterparts. This is not running as quickly as I would hope to, but that's fine. Without further ado, and taking the most of what we can have out of this day, a small description of the workshop. Sigrid and Johannes have come after doing specifically a tour of Australia, hit the workshop on Monday towards a robotic KUKA robot that we had acquired only very recently, and helped us to set up an environment in which we were able to learn about the dealings of that robot, because that is not something that comes easily. That is not something that is very available or has been very available to us. And at the end of that workshop, we have a better understanding of what could actually take place in architectural design as well, as to how to translate that architectural design into interfaces in which the robot manufactures according to specific toolpath and to specific cuttings. That takes into account not only an ability to work and design through these environments in Grasshopper, but it also takes into account an interface that the Association for Robots in Architecture has developed for the KUKA, which is a complete novelty on the market, and which is something that is extremely powerful because it enables people to go directly from their design and scripting environments towards an execution. That's the KUKA PRC, and that is something that they are very generously distributing throughout the world. Now, the Association for Robots in Architecture is also something that is very unique, not only the program that they are so generously offering, but also the person who are the drivers behind that association. Sigrid Brell-Kotschan and Johannes Braumann have established the association in 2012, and they have initiated this association in order to support institutions, to support manufacturers, to support a general community in the ways of understanding the work in and through the robot. In a way, this is almost a manifesto that they help setting onto the track, because the philosopher Wilhelm Flusser, around 1920 in Prague, already had come up with a vision of an architectural environment, both in practice and academia, where he basically foresaw that we are, rather than letting the robot serve us, we'll work closely together in universities that will be very different from the universities that we have been used to, in order to exchange design processes, design technologies, design methods, manufacturing techniques, and most importantly of all, possibly an archiving of historic craftsmanship that would be lost if it would not enter the processes through robotic manufacturing. So I would like to invite now Sigrid and Johannes to come up here and to give us the keynote lecture. Thank you very, very much for joining us. It has been an extreme pleasure and very heartfelt welcome again to the University of Sydney.
Well, thank you very much, Dagmar, for this really great introduction. We duly feel very welcomed here, and we had a very nice time so far in Australia, and especially also in Sydney. So the association, as you mentioned before, was founded as a spin-off association of Vienna University of Technology for Applied Research with industrial robots, and we have been developing KUKA PRC, which stands for Parametric Robot Control. And since 2011, we are also a recognized KUKA system partner. So the idea of the association is not only in helping education and the development for educational projects with robots, but it is also the idea of applying research within architecture, within the creative industry, but also cooperating with construction, aeronautical, automotive, and composite industry. So in the last 24 months, we were lucky to be a co-applicant and a research partner of research projects with a total volume of more than 3 million euros. And we have also been verified as a research institution, not only by our local research developers, but also by the EU. And we've been verified under the EU FP7 SME call just lately. The idea of this association started really in a very little community just surrounding the European institutions. But as you can see here on the map, I mean, it's not a very recent map, as we get nearly news from institutions on a daily basis that new robots have been supplied for education. And also you can see in Australia we have already marked RMIT, but we still have to mark University of Sydney, and hopefully we are also going to have another dot for up in Brisbane at the Gold Coast for Bond University very soon. So the idea really started in Europe, but as you can also see in the US, especially at the East Coast. There are a lot of institutions who have already robots and who use robots in their education, in their curriculums, and also in research. Robots in architecture is not only a platform to exchange ideas, but it is also a hub for everybody interested in robots, so not only educational institutions, but we also work together with a lot of artists and also with architects. And as you can see here, that we also promote whatever is been doing with robots via our Vimeo channel or also via Facebook. So we are also posting projects from all our association members. And also on this map, you can see that there are very little white dots left on the world map who have not yet been downloading one of our videos. In last year, we had also our very first conference on robotic fabrication, architecture, art and design in Vienna. What you see here is the proceedings, and the idea of this conference was to invite international recognized institutions to open the research labs with robotics and to open these labs for the public, so that more than 100 people were able to attend robotic workshops and get the actually hands-on. These videos have been downloaded since December 2012 for more than 200,000 times. So you see that the recognition worldwide is really high for all these research institutions. So just to name a few of them: TU Delft in the Netherlands, SciArc, of course ATH and Rob Technology, so this is one of the more famous because they have been starting publishing very soon. Then also the University of Stuttgart with Achim Menges and his team. They are also recognized for the big projects doing pavilion size. But what was also very interesting was that when we started researching, we found out that robots have already surfaced in the construction industry for quite a long time, but have not been public. So what you see here is actually an Austrian steel manufacturer who uses robots to provide robotic or also steel manufacturing know-how worldwide. So what they realized is that they have to shift from purely manual work to automation, and then later on, because also the job situation was very hard in Europe, so what they do now is they're not fabricating anymore in the Austrian headquarters, but they create robotic automated machines to be able to, for instance, automate the welding and the assembling of steel girders. But what are industrial robots? So we are not talking about the humanoid robots. We are talking about robotic arms, which have freedom of 6 degrees due to the 6 axes. And what makes them so interesting, especially for the creative industry, is that it doesn't matter if you have a small size desktop robot or a really big robot that can lift a car chassis, because the codes can be scaled to each robot. So this makes it really interesting for prototyping, as we know it from architecture, for instance, scaled model and then blow it up to a one-to-one scale. So where do we come from? Actually, as Dagmar has said before, we are actually architects. So what you see here is an architecture project that our office has won just in 2011. And to be able to produce and manufacture these such projects, we do need a highly understanding of fabrication technologies. So Grasshopper, as one of the interfaces for Rhino, we do not only use for design, but we also use it as a very valuable optimization and analyzing tool. So what you see on the left is a NURB surface for non-uniform rational B-splines that you would usually create in a CAD environment, and you realize immediately when you just analyze the main girders and also the secondary structure that you just would not produce something like this. So in the middle you see the optimization that was done by programming. So, and then on the right you see the planarization. So what is very interesting to former times is that the project that you see here has been, I just have to start this, has been created not manually, but it is a computed surface. We can analyze panel size for instance, efficiency, and then also have the layout for the fabrication directly from the CAD environment. And then what was even more interesting with this project, that we were starting to talk with contractors, and we always like to mention that we also like to play with robots, and all of a sudden they say, oh, we do run robots also in our wood workshop, come and see, because we are programming these robots in Excel sheets. If you can do it better, then just let us know. What you see here is not a small machine with a small blade. Like this blade has a diameter of about 1 meter, so this is a massive machine here. And they have been producing wooden panels like since 15 years. And yeah, so the idea of also streamlining the process from a CAD drawing to the machine is not only interesting for us architects, it's actually also interesting for industry. So the next project, Johannes will run you through. This is one of our bigger projects that we have been doing in 2011. And so I just want to hand over.
Yeah, so just to move from an architecture large-scale project to, for robotic scale, is also a very large project. This is the Red Bull Arch. It's placed in Spielberg in Austria. Red Bull is an Austrian company, so they were invested here, and they a few years ago bought their own racing track in Austria, which we've just learned that is going to be used for the 2014 season of the Formula One. And they probably, in aspect of this event, they commissioned two artists, Clemens Neugebauer and Martin Kaldorfer, to design a kind of monumental landmark sculpture, something that keeps the track recognizable in TV or also from the outside. What you see here is basically a structure that is 70 meters high, 23 meters wide, and it consists of two distinctive parts. In the middle we have a steel bull. It's made quite conventionally with an internal structure plated with two-dimensionally cut corten steel, which is then assembled on site and was done with regular CNC machines. What's quite interesting, however, is the arch that goes around it, because the artist decided that they didn't want to have this kind of substructure and structure. They wanted to build a more or less massive arch consisting only of aluminum. So what they did is they created this kind of twisted design. The arch is actually a complete freeform, non-developable, and not really easily dividable. And they set it up in about 20 sections, each consisting of 4 aluminum elements. So they were required to fabricate about more than 80 elements that are larger than 2 by 3 meters in size. And as you can imagine, this is no small task. So what happened is that they looked for ways how they could actually fabricate such a complex surface. Because, as you may see here, and I'm already spoiling how they fabricated it, this is not just having this kind of small molds or whatsoever. These are massive molds, but at the same time aluminum is very expensive. So they have a very elaborate substructure. They have this grid in the middle, and on the outside they have a completely double curved surface, which also has to be fabricated. So when they approached with such a design for the aluminum molds, when they approached contractors, they were quoted very high prices. So they actually started looking for alternatives, how they maybe themselves could even fabricate these complex parts. And through the research, they finally came across the work that was done at that time at TU Vienna, where a milling robot, very similar to the one that's used downstairs, was used to fabricate larger scale foam models. These artists were very enthusiastic about it, and what they did is that they just immediately went to Germany to a large automotive company and bought a huge used cooker robot for the very small price of just about 25,000 euros. So this is also a very good advantage of robots. They are used in industry, and when they're phased out, you can acquire them quite cheaply. However, the problem that they then came across was actually the robot standing here and set up, but the workflow didn't work as they expected. They wanted to have a workflow similar to what's happening with 3D printing. So they designed all their 3D meshes and then had the idea that they would just send these meshes to the robot and the robot would fabricate it. As you may know, with subtractive fabrication, the milling is not as easy. So they, to fabricate a piece using CAD and CAM software for milling, you usually need some kind of CAD program, then you need to generate toolpaths, then you need to simulate them, and so on. So for them, this was quite a shock when they discovered that it's not enough just to transfer the files to the robot, but that they would actually have to buy software that would be in excess of 30,000 euros, so actually exceeding the price of the machine itself. At that time, basically, they were made some further research and got in touch with us. And we finally managed to find a way to work with them that we would create an interface for them that would allow them to fabricate these pieces by themselves. So how this worked out was not in a way that we would do all the programming basically in Vienna and then send them the files and they would just press play. But we decided on a way of knowledge transfer. So this happened in a way that we taught them for just 1 week or 4 days how to use the software, how to use the kind of special interfaces we developed for them. And after that, they were actually able to fabricate these pieces by themselves without actually requiring much more help. So we came there, we taught them how to use it. Then we actually didn't hear anything from them for quite a few months. And then when we really didn't know if this would happen or not, we got a call that they were done fabricating. So just to walk you through a few of the steps that were required. So first, they would mill the pieces using the custom workflow developed that was based on our software Cooker PLC. They even improved the process. They started out like that, with the piece milling in front of them, and then they would have to turn it around, mill the other side, then they would have to flip it, mill that side, then would have to turn it around again. So they themselves actually then optimized the process by having the robot basically bend over that way, have a vertical standing piece, so that the elements would fill the spherical workspace of the robot as good as possible. So they were even able to innovate and enhance the process. Afterwards, the pieces were then shipped to Germany, which was again quite a challenge. These ribs are 40 millimeters wide, approximately. And so this is a challenge for fabrication to get it really accurate. What you don't really think about, this is also a challenge for transport. So quite a few of the molds actually broke during transport to Germany and had to be redone. They were then placed in a mixture of epoxy and sand and cast using a method called lost foam casting. So basically hot aluminum is poured onto the foam, dissolving the foam just into fumes, taking the place of the foam, and then hardening. Pieces were then assembled directly on site at the Spielbergring to get a feeling for the size that was required. It was quite a massive task for them, but we're really happy to see that they really managed to do that. From a software side, usually if you want to do robotic milling, you get a workflow like you see here on the bottom. So as I said before, you have to do your design in computer-aided design, then you move on to milling software, then you move on to robot simulation software, and then to the robot. So if anything happens, if you, for example, in the simulation, see that you cannot reach a certain point, you may actually have to go back to a geometric design, change it, then do the milling strategy all over again, then simulate it again, and then hope for the best that it would actually work. This process is quite expensive from the software side, and it's also complicated. Just have to learn not just one software, but actually to have to learn 4 types or 3 types of software. So you actually have to think about the person who did the manufacturing at the artist was the artist's son, didn't have any experience with CAD, CAM, or machines. He actually studied tourism, but he still managed to fabricate it. So this was really our task, to put all of this in a process that is as easy as possible. So if you have seen Grasshopper before, in Grasshopper we have this kind of plug-and-play process. We unplug and plug certain components, and we try to apply the same concept basically on robotic fabrication, that we just create our tool paths or whatever parametrically in this kind of parametric design environment, and then we're able just to immediately simulate what's happening. We exchange tools, we can exchange robots, and we see the effects that this is going to take. This is quite suitable to industrial robots because robots go beyond the scope of regular CNC machines. This is not just about milling, this is also about crimping. This is just a basic multifunctional machine where the function is basically determined by whatever you put in front of here. So there is the need for dynamic programming environment. While you can do robotic milling with state-of-the-art CAM software, if you want to do stacking or hot wire cutting or whatsoever, you run into the problem that there may not even be a software, even a commercial software that is available to do these things. So this kind of programming also has some kind of advantages over regular, if you call it script-based programming, where you think about, for example, you have your code, you go through the code from here to here, then you evaluate, did it work or did it not work, and then you basically do this all over again. With Grasshopper and visual programming, we have the advantage that all these modules are basically solved in real time. So if you change anything with the design, you immediately see the effect that it has on the robotic simulation. So just like taking a digital image where you immediately see what went wrong and what didn't went wrong, you have this kind of instant feedback that allows you to evaluate and to learn from your mistakes much quicker than having to go through all this process, put it to the robot, see if it works, and then go back again. So this instant feedback makes the workflow quite a bit easier. So this was basically what we did for the artist. We just evaluated a few methods that they would have to use. They would use external NC codes, they would use flank milling processes to cut the sides, they would have to do 5-axis milling, and we enabled them in a way that they would really just have to reference their data, simulate it, get this kind of instant feedback, and then put it immediately in use to the robot. So this was kind of a static workflow. So this is just referencing, getting an output. We got into this project quite late in the game, basically, where all the data was finished. They weren't really in a position to change the design or anything. So this is something that we like to show. This is our idea how this could have even been developed from the very beginning, where we do not just have this referencing and whatsoever, but that we actually have a parametric design that responds to the fabrication and to the changes the designer may want to make. So this is something basically that you know from generally Grasshopper. You have your parametric design, you have several values or constraints, you move it, the design jumps along with it. If we take a look at Grasshopper, this is this kind of visual programming environment. So we can change several parameters and whatsoever. This is quite regular. The thing that is special about that now is that we're able to couple this with the robotic fabrication. So what you actually see here at the robot itself is that it's dynamically adjusting to the changes you make to the design. So you make it higher, the individual parts get higher, and the tool partners immediately react to it. So also, if we go through the elements, you see that they are immediately referenced. They're fabricated with the same fabrication strategy, so they can be extracted. Then the process can be simulated, backwards in that case, first the top, and then cutting out the sides. So this links the fabrication with the design and able to flexibly deal with the design, but then also with the fabrication. What makes it even more interesting is that this works basically in real time. So you have your file like here, then you change something, and whoop, where is it? Anyway, and it's immediately updated. So you see here in the folder, do we have it? Just a second. You may already think what's coming when you see the folder name. So here, you see this is the file that drives the robot. So if we open it, and of course it opens in the other window, if we open it, these are the files that we give to the robot that just contain a series of movement commands. Now, if we enable the mass customization option here, that's what you get for working with multiple screens. We have here these output options, and then if we switch that one to automated file numbering, what happens is that this enables us to directly generate all files immediately. So what just happens if I push the slider and access the individual variations of that particular design, for every file there's a file, for every variation there's a file being generated, allowing you to quickly produce the data for fabricating all the pieces of a parametric design. So just to finish this aspect up, I don't want to spoil too much about the project that you're going to see afterwards fabricated. So Guido will present it to you, and about the robotic fabrication. But basically what the idea here is that you're fabricating from two sides. And this is quite a tricky proposition, because it's not a problem that the tool would collide with the material. The problem is actually the reachability of the robot, how far it can go, and so that the wrist of the robot doesn't collide with any of these wooden parts on the side. So we actually had the problem that whenever we changed something on one side, it wouldn't work again on the other side. So for example, if we have our angle that is somewhere here, no, it's okay. You see, you immediately start running into very strange design, but also robotic positions. And whenever we fixed something on one side, we had the problem that it didn't work on the other side. What we finally decided to do is that we just link these two processes. Even though we don't have two robots, we just linked them at the same spot so that we were able to evaluate all robotic positions at the same time. So whenever we change something to the design, we're able to see what's happening. And this is a fully parametric workflow. So if we say, well, we can go through variations, and every variation we immediately get the fabrication code, and we can immediately evaluate it from two sides. If you were to use regular milling software, you would at the initial simulation only see the very tooltip here and the tool holder. So now having this integrated full robotic simulation really allowed us to simulate the kinematics and to make sure that they don't collide. So we will actually see that in the final process downstairs later in the afternoon it comes up to 2 millimeters. So we're quite happy that the simulation seems to be accurate. So really further this is kind of, before we had this kind of static programming. Static in a way that we just replace the inputs. With this dynamic programming where you have the code react interactively, we have more possibilities both in design and manufacturing. We have this action and reaction, if you want to call it that way, in real time. Now what's interesting, this is from some kind of smaller project for the opening of the KUKA headquarters. We can then also start to implement in this real-time simulation and feedback not only the robot constraints, but also the possibility, the properties of materials. So actually in that case, video is working, video not found. Anyway, so in this kind of process, we actually have the robot pushing metal tabs in a 5-axis method, and we approximate the behavior of the material, and the robot's positions then follow this kind of material and implementing the material properties. So we do not just simulate the robot, but that we also are able to more accurately predict the behavior of not only the robot, but also material within a real-time visual programming environment.
So Johannes has already started to point out a little bit what our actual research is all about. The image that we show you now is probably how you know robots within the automotive industry. What we know now is that these robots have not really been fully used in their whole capacity and capability due to its multifunctionality, because here each robot has been programmed for a single task that it would do for its lifetime. So some robots are only holding, others are only welding, others are picking and placing. So actually the robots, like what they did is they have a multifunctional process, but they also multiplied the robot cells. So what we are interested in now is that we use a single robot or like 2 or 3 cooperating robots, and that we actually do a multiple functional processes. And one of our projects that we have been researching is with the material of spline text. That's actually a composite material also developed by a university startup of the University of Innsbruck. They have been interested in tubular structures where they actually pour resin to harden the material, but the material in its original state has totally different properties, like rope-like structures, very flexible, to more or less hardened structure that you could just bend. And what we do now is that we couple the material properties together with the robots. So for us, it's not what is really done in industry, that you have sensors and that the robot sees the material and how it's, for instance, bent and then knows where to grip. We go the other way around, that we say what we can do in Grasshopper is that we can incorporate physics engines and we can maybe predict how the material behaves so that the robot can follow the construction, and that we can also predict the output as a design. So what do you get when the robot is holding here and bending like that with this diameter and so forth. So this is one of our projects that we are working on now. And a first application, interesting enough, has come from the automotive industry, where they asked us to prototype a car chassis out of these carbon fiber tubes to be able to replace maybe the aluminum part or the steel part of the cars. And even though when we look at the video now, it looks like a very trivial process to wind such tubular structures, but actually when you look at robotic fabrication, the winding process is a process that is well applied and well researched into it. So what you see here is a prototype in a scale 1 to 5, and the idea or the task was how can they produce separate parts like window openings in an automated process, so that they can produce I don't know, 10 or 20 windows in one single process. So here you see that we use molds as the robotic end effector, and we also simulate the material, and when you watch very carefully, the virtual robotic process is very similar, or it's more or less identical to the physics output. This was done with a KUKA car 16, so that's about human size. But you can imagine when you do it, you can just blow up this prototypical process to a larger scale. So another project, or also what we like to do with the students, so now we are coming a little bit back to the educational environment, is that we prototype applied research projects also with our students. And what you see here has been done on a workshop in Venice. So what we are really interested is that processes have to be understood by the students. So in this case we have a polyethylene foil, and we have a heating resource and then a punching resource. And what we also wanted is that the output will be predicted in advance. And this is, for instance, coupling, for instance, KUKA PLC with the physics solver of Kangaroo. So the students could prototype their results first in the digital world and then test it also with the physical robot. The next project, I have to start. This was in 2010 when we, media not found. This was in 2010 when we started to prototype the whole process and also created previews from the geometry to the module, to the toolpath and to the finished project. These were modules which are more or less like 30 by 30 centimeters. So it's not too bad that this video is missing, but because like we had the chance about 1 week ago to do a similar process with RMIT students. And what you see here is that the whole design process was driven by the manual work of wire cutting. So what we did is that the students had to analyze different ways of how to drive materials through this wire cutting, and then these processes were prototyped so that the robot would do similar movements. Yeah? So the good thing is with education setup like this, that students actually do not really have to know how robotic processes are solved. Yeah? They only have to understand how material is driven through this wire cutting process, and then we reverse engineered the surfaces created by the tool, and then this was coupled with the robotic virtual environment and then also process. So what you can see here, these were the outputs for a couple of hours. So it was also a very, let's say, relaxing task, because in the end people just did something without thinking about what they were doing. Yeah? And also the manual work was really a great work. And we had first year students who have also not seen Rhino and Grasshopper or any other CAD program, and we also had last year students. So also this group was very diverse, and the great thing was that in the end you could not tell who was first year and who was like in his last year. And what you also see here is that we coupled different processes, like we pick a piece, we drive it through the machine, and then we place it and we stack it. We did not totally succeed in stacking because, as you can see here, the students had a further task not to waste any material. So also the mirrored piece was used. So they used actually both pieces. So due to the fact that we only had one robot, the second piece had to be mounted and discarded more or less manually. You see now somebody picking the second piece. So actually we could only stack one row, the second row had to be mounted manually. So we did not succeed totally in an automated stacking process. Next time maybe. So this is the picking, driving the material through the machine, and then placing it to the correct spot. So the whole production process was about 5 hours. So this would be ideal. And each one of the modules was actually a prototype, because these diamond shapes, they changed, and also the angles changed. So not a single part was redone twice. So we really had about 24 files for each single part.
Except the ones where people stumbled and they broke it.
And what was also very nice was the linear axis, because also you can do something like you can compensate singularity and also reachability problems. So you see we enjoyed just getting its butt shape. The next project again was this forming. So this is the process that has been applied first. So we also do form studies with the robots and with cooperating robots. So students develop through the manipulating of several robots different possibilities of form generations of a material like Splindex. So the idea to have robots in the education is that we can integrate robots now through the modular programming and by adding, unplugging and plugging different kinds of sources. So what you see on the right is the specific robot program, but it's really open to whatever generic you produce first. So we use it for our geometry classes, like understanding how kinematic works, understanding how geometry or what kind of geometries we can produce just by tilting, for instance, a milling tool, or by using different ways of driving, for instance, a conical milling tool through the surface. So these are also results done at Sydney University, what we call like these holographic images. And how this really works on a direct basis is also shown in this video, which was done for the KUKA CEE opening in Austria, where it was a live event. Images were taken by all the VIP guests and then processed immediately. So after 10 minutes, everybody has had their own little piece of art representing their own image. And here you see the conical milling tool and the different depths of the drilling with this conical milling tool actually made these images becoming in different grayscales, black and white. And it was a real nice event, and everybody liked how the robot processed their own images close to real time. So in the front you see all the KUKA representatives from Germany and Austria. So the geometry via robotics is a really hands-on experience with geometric properties, and they have a great education value. The intelligent use of geometric properties such as developability, offset or ruled surfaces, they are a great relevance not only in education but also in modern architecture. We have another project which is called Robotics, which is gender-relevant programming with kids from 4 years to the age of 18, where we use robotics for the easy interest of mathematical, technological background. And as you can see here, kids are fascinated. They have no fear to drive the robot like an iPad. And it's also a great motivation tool in whatever situation we are. So also with our students at TU Vienna, like the whole setup, also that we've experienced downstairs, that you build your own little gadgets and how to set the robot and the stock model and the material. So also downstairs, what you can experience later on, we have been pushing the limits. And so I would really also thank the great team around Marjo and Dagmar with Gabe and Mel, so for helping us setting up like a really great clamp table. So even though you are newbies, we have seen new applications. So I want to congratulate for just plunging into the big pool. And to finish off, so we are open for discussion and for questions. I also show you one of the images or videos that we have been producing with one of our first workshops, where you can see also a different range of what can be done. So for the robot, it doesn't matter if it's 3-axis movements or whatever it does, because it's always 6-axis. So yeah, have fun with this video, and if you have any questions, we can start answering now. Thank you very much for your attention. this was in Berlin, as you can see, Berlin and graffiti. So this is also something that you can do easily just by coupling spray gun together with Arduino and the robot. I think they were not really pleased that we actually spray painted the white wall. I couldn't handle it doing it on the paper. But it was an art school, so it was fine. And as you can see, you can also optimize the output by changing speed and things like this. So our manual linear axis. So this will be something for Sydney University with the little gadgets. So hiding in the back is Bob McNeil, like the founder of Rhino. And of course, I also want to thank David Rutten for providing such a great interface like Grasshopper to be able to put on top.